Thanks for the invitation to speak here. Very happy to be back in Vienna after 11 years since that World Cup final. Okay, so I'm giving this a talk about very old results. So I apologize. I guess I see a lot of new people. I thought many people in the audience have seen me talk about this in the past. Hopefully they don't remember. So maybe new again. Because it's kind of the, I don't know if it's the last time I worked in reverse math, but probably the one time I worked in reverse math and higher computability at the same time. So okay, instead of going for something newer, I went for something more appropriate to the topic of the course. One thing that I didn't do when I was giving this talk before is say something a bit about how higher computability shows up in the proof, because that's more into the proof. So the last third of the talk will be showing some of the ideas that show up in the proof. I won't go much into detail because they are very technical, but at least a little bit about where this kind of alpha computability or higher ordinal computability shows up, or at least in the proof. So the idea for the proof is like the first third is going to be on kind of more like a historical background for the problem. Then the middle third is about our results. This is joined with Richard Shore. So explain the results in the second third, and the last third will be about some ideas in the proof, but from a higher viewpoints, not going into details. All right. So, okay, the first slide, I usually don't give it for, I give it for when it's non-reverse mathematicians in the audience, because it's kind of the motivation for the talk. So the question that we are set to answer, which is how much determinacy can be proved without using uncountable objects. Of course, that's not the question. We answer some question and then we figure out what is the question that we answer and we put it that way. No, this is how it usually goes. But we were working in reverse math, so we were not thinking about how much can be proved with uncountable objects. But I think it's kind of interesting to set up the question like this. And the reason why this is essentially reverse math is because CFC without the power set axiom is conservative for pi1-4 formulas over second order arithmetic. They prove exactly the same pi1-4 formulas. You could argue that CFC without the power set axiom is essentially CFC without reaching uncountable objects, just staying in. Like you get an infinite set, you get omega, you get the countable things, but you cannot go beyond. And determinacy statements, I'm going to explain what they are exactly, because since they are the main topic of the talk, it's good to know, to have everybody on the same page. So if you don't know exactly what they are, I'll say exactly what they are in a second. All these determinacy statements are pi1-3 statements. Most statements in mathematics are even below that. So essentially, CFC without the power set prove essentially the same. Well, they prove the same determinacy statements as second order arithmetic. So the question that we're asking is how much determinacy you can prove within second order arithmetic. If you're curious if this is sharp, yes, Pfefferman and Levy show that sigma 1-3 axiom of choice, which is a sigma 1-5 statement, follows from CFC without power, but it doesn't follow from second order arithmetic. So that's as far as you go. Okay, but that's a side note. Okay, so that's the question: how much determinacy you can prove? Okay, so let me explain. I mean, I know probably most of everybody here knows what determinacy is, but since I want to mention it in every single slide, let's get the definitions set up correctly. So what is determinacy? So the setup is that we have a game in which two players play alternatively forever, and they play natural numbers. When they finish playing, they end up with an infinite sequence of natural numbers. and you start, before starting the game, you fix a subset of the sequences of natural numbers beforehand. That's going to determine, that's going to tell you what the game is. And then you say that player 1 wins if this sequence belongs to the set, and player 2 wins otherwise. Okay, so you set the rules beforehand. Player 1 wants to be in A, player 2 wants to be outside A. A strategy is a function from finite sequences to natural numbers that tells you what to play next, given what has been played so far. It's just one function. If this will play so far, play this next. And a winning strategy is a strategy that wins, doesn't matter what the other player does. Always wins. That's a way to write out definition formally, but essentially that's what it is. It's just a function that tells you how to play, and that always wins. And we say that a set of sequences is determined if one of the two players has a winning strategy, if there exists a winning strategy for one of the two players. And this is the notation that we'll use. If you have a set of reals, okay, so reals, gamma in a subset of the power set of Baire space, we say we use gamma det to denote the statement every set in gamma is determined. Okay, so that's the basic setup for determinants. So we're going to be analyzing how difficult are these guys to prove, how far up can you go within second-order arithmetic. Let me tell you a little bit about the early history of determinacy in this setting. So one thing that makes determinacy quite interesting for logicians is that determinacy of a simple class of game can be very, very hard to prove. So you can, and that's kind of gives interesting examples because you have simple classes, but it requires a lot of power to prove it. Yeah, this type of games are usually attributed to Gale Stewart in these 53 papers. They show that open determinacy is true, and that full determinacy, like all sets, is false if you, and there's an important use of the axiom of choice in the proof. So with the axiom of choice, you cannot get determinacy for all sets, but yes for the open sets. Then this, the ball started rolling in the following years. G delta determinacy, or like both phase pi02 and pi03 were proved by Wolf and Davis. In 72, this got extended to pi04. These proofs get complicated. Open is nice and easy. This one, it takes some time to, and then here they start getting crazy. But well, yeah, these are fun, and they start losing the fun around pi04. And this is a pretty nice proof. This is fun. So Martin shows sigma 1 determinacy, but now not in CFC, using that sharps exist. He needs that for analytic determinacy. He needs to go a little bit beyond CFC. And then around the same time, I guess the years are the publication years. So I don't know the history of exactly what came first. So Harvey Freeman shows that for pi05 determinacy, you need to use at least the power set axiom at least once. So you need an uncountable set in the proof. And then iterating that idea, well, I don't know which one came first. He shows that to prove Borel determinacy, you need Aleph1 iterations of the power set axiom. This is still within CFC, but it's not common in math to see that you need so many iterations of the power set axiom. That's why that theorem was so important. And I guess what I heard from people saying is that, okay, when Martin saw that you need those many iterations of the power set axioms, he said, okay, how can I do a proof that uses those many power set axioms? And then he showed Borel determinacy a few years later within CFC using Aleph many iterations of the power set axiom. Oh, I don't know.
They use more than second order.
Yeah, no, it can be. It doesn't use. Yeah, it's beyond. It's beyond. Yeah, according to what we're gonna see here, it's beyond. And but yes, probably they were using.
Oh, I04 needs more than.
Yes.
Oh, I'm sorry.
But that's that's a result of the talk.
Actually, the name of Aaron's paper title was ZF.
Yeah.
Without choice. Yeah. Well, yeah. So you need to use. Yeah. I wonder how. Right. So probably. Oh, but this is right. This is after Harvey's, or maybe at the same time. So they knew they had to go use a couple of powers. Yes. And probably David's. I don't know what. Okay. Yes. I don't know that much about the early history. We're good in time. We're good. Okay. So. One thing that I guess I find it interesting for one reason for studying this, the consistency, the strengths of determinacy statements, is that they define a natural spine of statements. So we know as an empirical observation that natural statements or natural axiomatizations of math are well ordered under consistency strengths for some reason that is unclear. So this is a very interesting phenomenon that shows up in logic, and it feels like it's telling us something. In some contexts, like in the Turing degrees, there is a way of formalizing this statement and making it true. So, for instance, the uniform Martin conjecture, which was proved by Sleiman and Steele, says that if you consider certain type of functions, Turing degree invariant functions from the reals to the reals, which are that are uniformly degree invariant, then they are well ordered under comparability on a cone, and then there is some way of saying these two things are kind of similar. So in some settings, this empirical observation kind of has some mathematical footing. Another one is this result of Wedge, which is the Borel sets of reals are well ordered under Wedge reducibility, up to complements that are essentially well ordered. So it's another setting where you see this complexity structure being nice and well ordered. And Nemoto asked she published this in 2008. This idea probably existed before. So what is the strength of determinacy along the Wedge hierarchy? She wrote the kind of, I want like a program of understanding how determinacy, like we know this one is well ordered. What about determinacy statements along that hierarchy? How do they define? They will give you, we know this is well ordered, and now we translate this to kind of statements in second-order arithmetic, and we have now a spine of naturally defined statements. Right. So that's one of the reasons I think these kind of investigations are interesting. Okay, I say 2/3. I need to get to the second third. Okay, so in what are these? Some of these what was known about the proof theoretic strengths of determinacy. Here's a quick slide. Let me not spend too much time on it, but it goes from like open, like delta 0, 1. As the complexity goes up, you can see the theories that you need to prove them being stronger and stronger. Before we did our work with Richard, Philip Welch had analyzed pi 03 determinacy. That one doesn't have a full reversal, but He showed that he can prove it in pi 1-3 comprehension, but not in the system right below it, which is delta 1-3 comprehension. And Friedman's proof for pi 0-5, that pi 0-5 determinacy couldn't be proved in second-order arithmetic. Martin had brought it down to pi 0-4. So Martin knew already that pi 0-4 was not, determinacy was not provable in second-order arithmetic. And with Richard, we are set up to work on that double, between those two lines right there. So that's where we're going to be. Okay, and also so Martin had this unpublished book for like 30 years. It's still around. It's good. Not published, but it's still good. He claimed that CFC without the power set action proves delta 4 determinacy, but he didn't notice that, I guess he's not a reverse mathematician, so he didn't care. The proof uses induction on a predicate that is not definable in second-order arithmetic. It's a predicate that goes, it's not defined, I mean, yes, it's, yeah, probably not even in here. There's, even in CFC without the power set axiom, you cannot prove that much induction. But yeah, he's not used to thinking about induction being working so high up in the self-theoretic hierarchy. So he was, well, okay, fine. CFC minus implies delta 0-4 comprehension on omega models. I think that works. But still, that proof kind of, essentially reading that proof with Richard and finding that you need more determinacy is a way, okay, where can we do this proof? Okay, so what are our results? So essentially, like if you look at what the parts of that proof by Martins that actually work, you can see that given a natural number, 37, fixed natural number, the second-order arithmetic can prove that every Boolean combination of n boldface pi 0-3 sets is determined. So that you can prove in second-order arithmetic, but the larger the n, the more axioms you need. And with Richard, long ago, we show that second-order arithmetic cannot show that every Boolean combination of pi 0-3 sets is determined. So that's kind of the limit. You can prove it so for every single n, but not for all the n's. So we take that as, well, okay, and the same that can be said about CFC without the power set axiom. And essentially using some absoluteness results, you get this other way of, maybe a nicer statement, says a bit more. The following three prove the same pi 1-3 statements, CFC without the power set axiom, second-order arithmetic, and the scheme that every Boolean combinations of n pi 0-3 sets is determined for all the n's in the natural numbers. Over something, over this plus RCA naught, let's say. Be enough. So they have all these theories are the same, and you don't need all these comprehension axioms. Determinacy gives them to you. I don't know if it's sharp. Yeah, no.
Well, the last scheme, they're all
Could have fun here. Yeah, so it's sharp, yes. Between these two is pi 1-4. But this one is these are pi 1-3 statements, so yeah, you couldn't get beyond that. For this, yeah, this one doesn't allow you to get to pi 1-4. Okay, let's get finer. Get finer in the statement of those results. We're gonna need to use the difference hierarchy. The difference hierarchy of sets of, in this case, we're gonna use the difference hierarchy of pi 0-3 sets. We say that a set of reals is m pi 0-3, so m differences. if there are pi03 sets, so that your set, you can write it as A0 minus A1 plus A2 minus A3 plus A, and alternate those two. That's why it's called the difference hierarchy. And equivalently, X belongs, a real belongs to A if and only if the list I such that the real is not in AI is odd. Okay, you can see that those two were the same. I wrote this last one. Okay, one more observation is any Boolean combinations of pi03 sets can be written in this way for some long enough m. So the union of all these guys is the same as all the Boolean combinations. So this gives us a way of stratifying the Boolean combinations, this difference hierarchy. And I give this third line, this equivalence, because this allows you to extend this hierarchy through the transfinite. Now, if you have a transfinite sequence of sets of, say, length some ordinal, you can use the same definition to define alpha difference pi03. And if you do that, you get the next delta class. So in this case, you get delta 4. Okay, I guess it's a typo there. Delta 04, both phase delta 04 is the same as the union of all the alpha pi03. So this is, with the omega, with finite combinations, you only get a little bit of the way. You don't get all the way to the next class. Okay, so now we restate the question as what is the strength of n pi03 determinacy. So n's difference in the n difference of pi03 sets. Okay, so that's, I'm just saying what these systems are. Pi1n comprehension is, well, not second order arithmetic, is within second order arithmetic, we restrict induction and comprehension to pi1n formulas. And delta 1n comprehension is the same, but now induction and comprehension are restricted to delta 1n formulas. And our theorem, okay, so the first one is, following Martin's proof, we show that this match determinacy can be proved in pi1n plus 2 comprehension. Following the hardest part of the proof is to read Martin's proof from the book and then to figure out that everything works. But more than figuring out that everything works is to understand the original proof. And then okay, there are a few things you have to be careful here and there. So that's essentially Martin's. We didn't do that much. But then we show that if you go a little bit below to delta 1n plus 2 comprehension, then you cannot prove it. So that's our main result. And Philip had already showed the case n equals 1 that I mentioned in the slide at the beginning. So, okay, the corollary is kind of the theorem that we showed before. For a given, for all fixed n, C2 can show determinacy of the n difference hierarchy, but it cannot prove it if you put the for all inside. So Gödelian kind of. Okay, so now the next question is, okay, you have this in between, this is sandwiched in between these two theories. Can we get a reversal? Can we get, for instance, that this one implies that one? Well, we can't. Okay, no, it's like, of course you cannot. Okay, and that's just one of these general results, absoluteness results. So already Mensalen and Tanaka has shown that if you start from pi1 comprehension and you add even all overall determinacy, you're not going to be able to prove delta 1-2 comprehension. Right, yeah, so even if you add determinacy, but yeah, this is a pi1-3 sentence, and it's not going to allow you to prove more things. So with Richard, we showed, well, here, this theorem is in our paper. We write it down. Proof theories kind of knew this before. I guess, I don't know if they wrote it down. But, so I wouldn't call this as our theorem, but we had to kind of write down the proof. So whenever you have a true pi1-4 sentence, pi1n comprehension together with that sentence it's never going to allow you to go to delta 1n plus 1, and you also cannot go from delta 1n to pi1n. with a new sigma 1,4 sentence. So you're never going to get a reversal. Yeah, so Borel determinacy and all these guys are pi13 theorems of CFC, so hopefully true. So this theorem applies. So you couldn't do reversals. What about if you look at consistency strengths? And we know that, yeah, in consistency strengths, always all the natural statements are, the empirical observation is that they're always in a line. So that should be true. So yeah, it is true. So we do prove that. So in terms of consistency strengths, determinacy for n difference pi 03, yeah, does imply the consistency. Well, in terms of consistency, this one implies that it's sandwiched in between. And these are strict, yes, they're actually strict. Okay, so we can refine this theorem a bit better. So using beta models. Beta models is this is the right place to kind of look at the strengths of determinacy statements. So a beta model is a model for some fragment of second order arithmetic where the natural numbers are the real omega and the sigma one formula is absolute over the actual real. So obviously sigma one formula in the beta model that is true in the beta model is, well, that is true in the real world is true in the beta model. So, and given a theory T, we can write this statement, beta T, which says that there exists a beta model of T. And actually, the better way, like the bold-faced version, is for every real X, there is a beta model of T containing X. So we're going to use this beta of a statement to mean that there exists a beta model of that. It's kind of, it's stronger to say that there is that the T is consistent. It says that there is a model with these particularities. So Harvey Freeman had shown, for instance, that beta of RCA naught is the same as pi 1 comprehension, for instance. Saying that there exists a beta model of RCA naught implies already pi 1 comprehension. So they get a bit strong, but then after that, they don't grow as much. Another observation, I'll skip the proof because I don't have time, that if a theory S proves beta of T, then the pi 1,3 consequences of S contain the pi 1,3 consequences of T. And this is a usual argument. Going from a model, you go up, you go down a couple of times. We'll use that. Okay, so a more precise theorem now using this beta statement. Now we do get the reversals. So the n pi 3 determinacy is now sandwiched in between, and these are actual implications. So now we get reversals between beta of pi 1 n plus 2 comprehension and beta 1 n plus 3 comprehension. And these are all pi 1,3 statements. So if you move to that side, now you get reversals. So that kind of gives you a better way of stating where is this guy. Yes, you don't need this. Yeah. Yeah. Yes, you don't need this sub-zero. That's right. Okay, so that's the more precise statements that we get. Yeah. Okay, so let's jump to the ideas for the proof. We now have 15 minutes. Okay, so there is 3 slides. The ideas that are new to this particular, I mean, I'm going to show them in this particular case, but the first ideas are essentially due to Harvey Freeman's first proof, but just putting this in this setting. Okay, so the first theorem was that delta 1 n plus 2 comprehension doesn't prove n pi 03 determinacy. A connected question is given a class gamma, how far in Gödel's L hierarchy do you need to go to find the strategies for this game? What is the least gamma such that L gamma proves gamma determinacy? And essentially, in Harvey's proofs, more or less, there was something like the least gamma such that L gamma proves pi 4 plus beta determinacy is the least ordinal such that gamma proves CFC plus beta iterations to the power set. So that proof of the power sets that I mentioned from 71 stratifies like that. But we're now working with just below one power set. But the idea of looking at L was already in that paper. But now, since we're looking below C2, we need to look at L up to this kind of ordinals. And this is where the alpha recursion theory kind of shows up. So we say that an ordinal alpha is n-admissible. So this is an ordinal, a countable ordinal, if it satisfies any of the following equivalent statements. I'm going to give a couple of definitions. They are all equivalent. One is that L alpha satisfies sigma n minus 2 separation, like kind of the version of replacement, essentially. And delta n minus, no, separation is the comprehension and collection is the replacement. M equals n, yes, a good point. Thank you. Always m equals n. No. That will be confused. Yes, that's a good point. Yes, this m and this n are the same. That's the same thing. Saying that there is no sigma n definable in L alpha function from an ordinal below alpha that is cofinal into alpha. It's kind of like a regularity condition, right? So you cannot reach alpha from a lower ordinal in a cofinal way if you restricted yourself to sigma n definable functions. So it's kind of like regularity for sigma n. So this, why do we care about n-admissible ordinals? Is because in this setting, is because if you have an n-admissible ordinal and you look at the reals in L of alpha for that alpha, then that models delta 1 n plus 1 comprehension. And actually, if you take the least alpha n to be the least n-admissible ordinal, then that is also the least ordinal such that you satisfy delta 1 n plus 1 comprehension. But we don't need that here. Okay, so let's consider the least n-admissible ordinal, and we're going to be playing at that level. One observation that we're going to use is that the theory of L alpha n does not belong. It's a real, it's a binary sequence. This theory doesn't belong to L alpha n. And this is by Gödel, Starsky, and definability of truths, and the fact that all the reals in here are actually definable because of the admissibility. So all the reals are definable, so this one cannot be definable. So it's a real that doesn't belong to L alpha n. And what we need to do is to devise n minus 1. I'm shifting the n by 1, so I can use alpha n here, and the n minus n plus 2. So we need an n minus 1 pi 3 game where the players play sets of sentences. I mean, a set is just a binary sequence, so you have all the sentences, like have a Gödel number for each sentence, and you just have to say yes or no for each number. So that if one plays the theory, then of L alpha n, she wins, and if she doesn't, but player 2 does, then player 2 wins. That's kind of the one property that we need of the game. And then from that, you can show, using some absoluteness, that a winning strategy for the game must compute the theory of L alpha n. But the theory of L alpha n doesn't belong to L alpha n. So you can show, so that tells you that this model here, satisfies this much comprehension, but doesn't satisfy that much determinacy. Okay? So that's the idea. So we have the least admissible. We need to find a game like this. I have 8 minutes, so let me skip the techniques for the second theorem, and this is the last slide. What are the ideas for that proof? So again, let me repeat what we want. We want a game. It has to be in this complexity class, the game. Different hierarchy of n minus 1 sets pi03 sets, and it needs to satisfy that property, that whoever plays the theory of L alpha wins. And if both do, player one wins. And again, the first 3 or 4 lines kind of like mimic the idea in Harvey's proof, and then they get difference. Okay, so we say that each player is playing a set of sentences. So we have got all the numbers for the sentences. We go one by one, and we just say yes, no, which sentence you want in the theory. You're gonna end up with a set of sentences. You within your game, you're allowed to put the rules for the game, right? We are defining the game. So we are gonna make, they need to play a complete, consistent set of formulas. They need to satisfy CF plus V equals L alpha. So there is some way of writing down that V looks like L of alpha, L alpha n. Alpha n is the least n-admissible ordinals. See? And okay, so they are playing that, and we have to be able to define the game so that we can identify who is playing the theory of L alpha n. So if one of them is playing the theory of alpha n and the other one is not, we have to be able to identify that. But the trick is that we have to identify it with a game that is difference of n-1 pi03 sets. That's our restriction. So these are models of L alpha n where everything is definable. Every element is definable. For every formula, it has a definable element because we have a definable well ordering. So we can define kind of like term models. From a theory, we can define a term model. Like take all the definable elements, use the defining formula to talk about the element, and like in Gödel's completeness proof, you get a model from the theory. So actually, you get models of C equals V alpha n. And we need to identify who of the 2 players is playing the real L alpha n. If both are doing, we say play one wins, so suppose one is doing and the other one is not. We want to kind of, okay, and L alpha n is the only well-founded model of CFC plus V equals L alpha n. All the other ones are not. So we are assuming that one of them is playing a well-founded model and the other one is not. Okay, so so now what we have to do is using differences of pi03 formulas, we need to identify the player that is playing a well-founded model. Okay, so in Harvey's proof for showing that you couldn't prove by 5 determinacy in second-order arithmetic, instead of alpha n, he's using this beta 0 ordinal, which is the first ordinal that is not n-admissible, that is n-admissible for all n's, that is for which you have a model of second-order arithmetic, but he was using pi 5 formulas. And with pi formulas, you can write something that pretty much identifies which of the 2 models is the most well-founded of the 2. So it's easier in that case. You can say there is an ordinal in here, so that's in here, you can reach it from below, but it's not the same. You can play with the models and compare them with pi 5 formulas. But differences of pi 3 formulas, our hands are tied, we cannot write that sentence. So we cannot say exactly which one is the most well-founded of the 2. So we need to find something else. Okay, so here is where the difference shows up. So let L alpha be the intersection of the 2 models. And what we need to do, and I'm not going to tell you how, but so this line gets very abstract. So we need to find, so what we do is we find a condition. This is a pi 3 condition about the game, so and a property about the models, such that if this guy is, suppose that we know that alpha is k admissible for k below n. So k is, start from the beginning. So k is a small number. Suppose that we know that alpha is k admissible and that this property pk holds. This is a property about the model, about L alpha. It has a bunch of lines. Then this condition has this following property. If the condition holds, then we find a descending sequence of n. So the condition, you can deduce from the condition being true that n has a descending sequence, and in that case, you know that whoever play n lost the game, and you're done. You found the best model, the other guy. If the condition doesn't hold, then you conclude that alpha is k plus 1 admissible. and you conclude this next property. So now, by induction, now you go to the next, because now you know that alpha is k plus 1 admissible, and now you go to look at ck plus 1 and pk plus 1. And you look at the first condition that fails. Right? And these guys are pi 0, 3, so you're looking at the first one that fails, so that's why you get the difference hierarchy. Okay, and then, right, that's, I don't know if you call that alpha recursion theory when you're playing with these ordinals. That's right, yeah, good point, thanks. You're, sorry, yes, the first one that holds, that's the one you want, yes. And because when you find one that fails, then you know who won. Yes. Yes, yes. Thank you, Robert. Okay, so yeah, that's where you need to play with playing with these k-admissible ordinals, and the fine properties of L there show up in these reverse mathematics results. Thank you for your attention.